Now let's check the variance. Variance is very similar to standard deviation. You can check the definition. It's just equal to the square of the standard deviation. So S is our sample standard deviation, then S squared will be our variance. Okay, similarly, if sigma is the population standard deviation, then sigma squared will be population variance. So the relationship is just the same, no matter for sample and for population. Standard deviation is just the square root of variance. Variance is just the squared standard deviation. Let's check the notation. It's just the same notation. S is for sample. S squared is also for sample. So S squared is variance. Similarly, sigma is for population. Sigma squared will be the population variance. So first property of variance is, remember the previous measures have the same units with the original data value, but this variance is not the same. The unit of variance just the squares of the units of the original data values. And it's similar to standard deviation. Variance is also very sensitive, which means not resistant. So if we add one or two extreme values, variance can also dramatically change. Let's check. Of course, variance is the square of standard deviation. Squared number is never negative, but it also can be zero. If standard deviation is zero, then variance is 0 too, which means all the data values are just the same. No variation, right? But compared to S, compared to standard deviation, variance is an unbiased estimator. But S is a biased estimator. Of course, we like the estimator can be the unbiased one. So that's why we already have the standard deviation. We still want to use variance sometimes because variance is an unbiased estimator. So remember when we talk about the denominator of two different formulas of population standard deviation and sample standard deviation, we talk about the different denominator, right? So one for the sample, we use n-1, but for the population, we use n. Why we should use n-1? Because this is called degrees of freedom. For example, if we know we have n values, For example, we want to assign 6 values. And if we already know the mean value, for example, we want to assign 6 values and we know the x bar. We already have the x bar value. For the first value, we are free to pick any number we want, right? For example, you can use 6. For second value, we still can pick any number I want. I can pick 2. So for the third one, I'm still free to pick anything. Equals 3. x4, I just pick 4. x5, I can pick another 7. But how about the last one, x6? I'm not free, right? Because we already have the mean value. Mean value is 5, which means the sum of all these 6 values should be equal to 30. So we have the constraint for last value. So last value is not free to pick any value. So it will be 30 minus the sum of all first 5 values. So we will get the last one is 8. Right? The last one is not free to pick, but the first 5, they are totally free to pick any value. Only the last one is not free. So we will see the freedom, the degrees of freedom is just 5 for this example. And we have 6 as our sample size. Total we have 6 values. Degrees freedom is just 5. So degrees freedom is n minus 1 equals 5. Okay, so this is just talk about why it's n minus 1, not just n. Okay, so the second we will check if we use n minus 1, then s squared tend to center around the sigma square. So which means if we pick n minus 1, then sample variance s squared will be an unbiased estimator for sigma square. But if we pick n, then it's not centered around the sigma square. Will be underestimator. Will be smaller than the true value. So that's underestimate. So we need to use n minus 1. That's another reason. The first reason is degrees of freedom. The second reason is we do not want to underestimate. So if we pick n minus 1, variance will be an unbiased estimate. So let's talk about the empirical rule. So basically, you need to memorize this special numbers. Within one standard deviation of the mean, there are 68% of the values. 2 standard deviation, 95% of the value. 3 standard deviation, 99.7, almost all the value, right? Let's check the graph. So what does that mean? So if x bar is right in the middle of the whole data set, remember it's the measure of center, it's our mean value. And the standard deviation x bar minus 1, x bar plus x bar minus 1s, x bar plus 1s means one standard deviation away from the mean. So in this part, we approximately have 68% of the data. Let's check two standard deviation away from the mean. So that's from here, x bar minus 2x to x bar plus 2s. In this bigger range, we will have 95% of the data. So when we talk about 3 standard deviation away from mean, so that's from 3 standard deviation below the mean, x bar minus 3s, to 3 standard deviation above the mean, that's x bar plus 3s. So the green range we will have, so the last bigger part, we will have 99% 7 of the data in this group. We can check an example. If we know the IQ scores have a bell-shaped distribution, which means we can use the empirical rule. And we also know the mean value, x bar, or this is the sigma, because it's just said that the IQ score, so that's the whole population. So we will say this is the mu, this is the population mean. And we also know the population standard deviation is 15, let's say. What percent of IQ scores are between 70 and 130? Let's check the solution. So if we know the mean and we know the standard deviation, it's easy to get 2 standard deviation will be just 30. And we know this 70 is just 2 standard deviation below the mean. And this 130 is just 2 standard deviation above the mean. And the score 70 to 130 is just 2 standard deviation away from the mean. If these two values are the 2 standard deviation, away from mean, which means 95% of the values are between these two numbers by the empirical rule. We also need to learn another measure, which is called coefficient of variation. This one is just a little transform of the standard deviation. So the coefficient of variation, we just use the standard deviation divided by the mean, of course, times 100%. Then we will get it's just describe the standard deviation relative to the mean. So it's called a coefficient. And we always round the coefficient 1 decimal place. 1 decimal place.